Good morning, everyone, and thank you so much for this opportunity. My name is Zheng FU. I'm a postdoc working with Philip at LSCE. Today, I'm going to talk about the critical soil moisture thresholds of plant water streams. This critical soil moisture threshold of plant water streams is the breakpoint when evapotranspiration starts to decrease. As we can see here, the x-axis is the soil moisture, and where y-axis is the evapotranspiration, which is the fraction of energy reserved by the plants, and this energy is transformed into evapotranspiration. In theory, there is a soil moisture threshold between the ratio of evaporation and soil moisture. What it determines the existence is the energy limited or soil moisture limited. When soil moisture decreases, the threshold is a point at which the plant starts to transpire less because of water stress. When the soil moisture keeps decreasing, knowing this critical soil moisture threshold is very important because the plant will suffer from water stress and it cannot grow well, even die if the soil moisture always lower than this threshold. This framework for this soil moisture threshold is well understood, but in reality, we don't know what is the critical soil moisture threshold from the observations and the models. For earth system models, different earth system models show the different ratio between evaporation and the soil moisture. As you can see here in this figure, at the same area, this in the median of US. We can see here the different earth system models show the different ratio between evaporation and soil moisture, and thus different soil moisture thresholds. So this difference from different earth system models contribute to the uncertainty of predicting future climate, water sources, and land carbon sink. On the other hand, for the observations, ICOs in Europe and the Global Fast Tower Network have collected many fast tower sites in the world, and this fast tower mirrored both the latent heat flux and the sensible heat flux, providing the opportunity to quantify the soil moisture threshold using the relationship between evaporation and soil moisture. For example, here we focused on the soil dry downs, which is defined by the soil moisture keep decreasing for several consecutive days with no rain. For example, during the dry summers. So we can see here the y-axis is soil moisture, while the x-axis is the days after rainfall. So after a rainfall, we can see the soil moisture keep decreasing for several consecutive days. So there are many soil dry downs at this site. So we can see here, and we can using all of these soil dry downs and calculate the evapotranspiration using the latent and the sensible heat flux, and then plot the ratio between the evaporation and soil moisture, and then we can detect this critical soil moisture threshold based on the ratio between the evaporation and the soil moisture. So at each site, we can collect all soil dry downs and quantify the threshold. During the dry down, the evaporation remains relative steady state at the first. As you can see here, this green line is the evaporation. So when soil moisture becomes low, then a threshold, the evaporation will decreases with soil moisture decreases. So at each side, we can quantify the soil moisture threshold based on the evaporation and soil moisture. But these observations are still limited because there are only few sites in some area, like the tropical areas. So currently, there is no observed global map of evaporation. So we need to consider other methods to get the global distribution of soil moisture threshold. Another method has been reported to detect the soil moisture threshold is using the ratio between the land surface temperature, diurnal amplitude (DST), and soil moisture. So we can see here the blue line is the soil moisture during the soil dry down. The green line means the evaporation, while the red line means the DLC, the land surface temperature diurnal amplitude. So increasing the land surface temperature diurnal amplitude in water limit region can reflect the increased partitioning of surface energy towards surface sensible heat flux. Therefore, the DST land surface temperature diurnal amplitude is positively associated with sensible heat flux, but negatively associated with evaporation and soil moisture. During the dry down, the DST keeps stable at first, then increase with the soil moisture when soil moisture is below a threshold. So here using fast tower data, here we first quantified the threshold using both evaporation and soil moisture and DST and soil moisture method respectively. You can see here figure A showed the soil moisture threshold using the evaporation soil moisture method, while the figure B showed the soil moisture hold using DSTL soil moisture method. On this side, we found the threshold from these two methods very closely, about 0.19. Then we did the same analysis for all fast tower sites and compared the soil moisture hold from these two methods across all sites. We found that the threshold estimated from the DST soil moisture method is similar to that of evaporation soil moisture method. So the DST soil moisture redshift can be used to quantify soil moisture threshold. To map the global threshold, we use the three soil moisture products from satellite observations, including SMAP SCAV, SMAP IB, and smooth IC products. The temporary solution is about 1 to 3 days. For land surface temperature, we use the Copernicus land surface temperature and MODIS land surface temperature. So right now it's defined as at least 4 or 5 consecutive day overpasses for smooth and SMAP soil moisture respectively. And we can here there is the result. Here is the distribution of diurnal land surface temperature diurnal amplitude DST and the number of soil dry downs. We can see the global pattern of the DST calculated from MODIS much well with that of Copernicus LST. And for the three soil moisture products, SMAP IB, SAV, and the smooth IC consistently showed the global patterns of the number of soil dry downs per year. The areas with the most dry downs are Central American, Argentina, Central Europe, and the Eastern Australia. So using this soil moisture data and the DST during the soil dry downs, we then quantified the soil moisture for each grade. We can see here the three soil moisture datasets: SMAP IB, SAV, and the smooth IC, and the two land surface temperature, Copernicus and MODIS, showed very consistently the spatial patterns of global soil moisture hold. For each grade, we quantified the soil moisture hold and the uncertainty standard error. So this soil moisture products, this three soil moisture products and the two land surface combined with the three estimate of soil moisture hold, combined yield 18 soil moisture hold ensemble members. The median soil moisture hold and its uncertainty across this ensemble member provide a global mapping of soil moisture hold based on a symbol of different satellite observations. We found that in this figure, the low soil moisture hold are mainly distributed in dry land existence, such as the western US and South Africa and Australia. However, the high soil moisture hold value usually occur in the wet region like the tropical rainforest and the southeastern United States and the southeastern of China. We also compared this satellite-derived soil moisture hold in the global map with the first tower derived soil moisture hold. You can see here the y-axis is the satellite-derived soil moisture hold, while the axis is showed the first tower estimates the soil moisture hold using the DLC method and using the EF method respectively. So we can see the satellite derived soil moisture is comparable to that estimated from first tower measurements, although their footprints are different. We also look at the soil moisture hold among different biomes. We found that the dry shrublands have the lowest soil moisture value, while it is the highest in the tropical rainforest. Existing in dry climate like the dry shrublands, dry grasslands, and dry savannas have the lower soil moisture hold than the wetter climate like the temperate climate, tropical climate, and boreal climates. Forests have the high values of the soil moisture hold than that of no forest existence like the shrubland, grassland, and the savannas. For the croplands, the cropland is very important for yield, but it's also strongly affected by management. We found the rice has the high soil moisture hold compared to the maize, potato, and the wheat. We also found the soil moisture hold in cropland tended to increase with increasing the fraction of irrigation areas, but this threshold in cropland tended to decrease with the increasing the cropland expanding. So the threshold in the cropland is also affected by the human management. We can also see the larger variation for the soil moisture hold even in the same biomes, indicating there are other factors to determine these soil moisture values. So we then analyzed the soil vegetation and the climate factors using the random forest to understand the drivers of the spatial variability of soil moisture holds. We found these predictors can explain 74% of the global variation in soil moisture hold. LDT index, leaf area index, and soil texture, like the sandy fashion, contributed most to the global variation of soil moisture hold. LDT index is defined as the ratio of annual precipitation and the rotational evapotranspiration. The partition dependence plot showed the LDT index has a positive ratio with the soil moisture hold. And the leaf area index also increased considerably with the soil moisture hold, but the soil moisture hold decreased with the high sandy fraction and high leaf nitrogen. Precipitation frequency has positive contribution to the soil moisture hold, while the global shortwave radiation negatively contributed to the soil moisture hold at global scale. So we have the global map of soil moisture hold. So what can we do using this global map of soil moisture hold? So here are to explore how many days in a year that existence are water limited. We calculated the fraction of time when soil moisture is below the threshold, which is defined as the ratio of the number of days with soil moisture below this soil moisture hold to the total observed daily soil moisture in a year. We assumed that the global soil moisture hold is unchanged with time, or it has a lower temporal variation. with the time. So we found the satellite observations showed the fraction of time when soil moisture is below this threshold. It's larger than that of the ERA5 real analysis soil moisture data. The larger fraction of time when data water limiter is mainly occurred in the dryland systems, such as in the western US and South Africa and the Australian. So the same analysis was performed for the daily ERA5 real analysis soil moisture data, and we found that the magnitude of the fraction of time below soil moisture hold is smaller than that of satellite observations. However, the global pattern of the fraction of time below soil moisture hold calculated from ERA5 is similar to that of satellite observations, which give us confidence that we can explore the long-term trend of the fraction of time when soil moisture is below threshold using the ERA5 data. So we then using this ERA5 soil moisture data from the 1979 to 2020 and quantified the soil moisture threshold below this quantified the fraction of time below the soil moisture threshold, and we found that this trend in the global fraction of time spent in water limit state has been increasing over the past 40 years, indicating that the terrestrial existence are shifting more time towards water limitation. During the 1979 to 2020, the increasing rates of fraction of time below soil moisture threshold are about 4 to 7 days per decade. The increasing rates are large in current region with low fraction. Then in current regions with the high fractions of time. Globally, the fastest increase in the fraction of time not only across in dryland systems like the Western US and the South Africa, but also occur in the some wet areas like the southeastern of China, the southeastern of China and the Indian region. In conclusion, we showed that the satellites observed daily land surface temperature and soil moisture can be used to map the global critical soil moisture threshold. And the low soil moisture threshold value dominates in the dryland system, while the high soil moisture threshold most occur in tropical rainforest. We quantified the global drivers in controlling the spatial ability of soil moisture threshold. We found global variation of soil moisture threshold in natural existence is mostly explained by aridity index, leaf area index, and soil texture. But soil moisture threshold in cropland is also affected by our management, like the crop type, irrigation, and the expansion areas. The global distribution of the fraction of time spent in water limited state has been linearly increasing during the past 4 decades. Okay, that's it. Thank you for your attention. I'm happy to take any question or comments. Thank you so much.
Can start with one question. So you found a very good relationship between the different methods you use to estimate this critical soil moisture threshold, Zheng. But you also found some discrepancies between the estimated values. How do you explain these discrepancies? And finally, in your view, what is the most accurate method for estimating the soil moisture threshold? If we have the choice, what is the best methods according to your experience?
Well,